Good morning. The third Sunday of the month, 11 o'clock means it's time for Chai and Why from Ruparel College. And we begin our series of Chai and Why sessions that cover the Nobel Prizes for the year. And we're going to begin today with the Nobel Prize in Chemistry. And to tell us about that is Jyotsna Kumari from the Department of Chemical Sciences at TIFR, where she works on materials chemistry. Her work actually is on trying to convert carbon dioxide in the air to more useful chemicals. But today she's going to tell us about the Nobel Prize for the year. Now, she is actually from a small place about 120 kilometers from Jodhpur. She came to Jodhpur after her 12th standard and did her BSc and MSc from there, and then came to TIFR, where she is a PhD student in the Department of Chemical Sciences. Online audience, please note that the only way we can get your feedback is if you enter the questions and comments in the chat. So please do so. We will monitor the chat and take those questions up. Of course, here you can ask questions. So we're going to learn about something very interesting, something with lots of area and whatever else.
Yes.
So seems like an exciting stuff. So just remember, there's no audience for there's no microphone for here. The mic is only for the online audience.
Okay.
For here, you'll have to just be loud enough.
Okay.
Okay. So on that note, by the way, I should also tell you that November is a month with 5 Sundays. So November 30th, we will have the Nobel Prize in Medicine or Physiology on the immune system. That's going to be discussed. And usually it's online only, but this time it will be in person at St. Xavier's College as well, because it's a special Nobel Prize session. And after that, the first Sunday of December, we'll cover the Nobel Prize in Physics. That will be at Prithvi. So the next couple of sessions are going to be on the Nobel Prize. But right now, the Nobel Prize in Chemistry, Jyotsna.
Thank you. Thank you, Arnab.
Okay, wait, we have to, are you share? No. We have to share screen, right? Yeah. 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 Okay. I hope you can see that. I'll try logging in.
Thank you, Arnab, for such a kind introduction. I'm Jyotsna. I'm from TIFR Mumbai. I'm a third-year PhD student. And in today's presentation, I'm going to talk about this year's Nobel Prize in Chemistry. So, title of my talk is Bridging Metals and Molecules, the Nobel Journey of Metal Organic Frameworks, in short, MOFs. So, this year's Nobel Prize in Chemistry is given to the development of a new category of molecules which are called metal organic frameworks, MOF. And in this talk, we will cover what are MOFs and what is the chemistry behind MOF developments, how they look like, how they behave, what are their applications. And but before going to that, let us just get introduced to the press. Okay, thanks. Okay. So let us just get first introduced to the scientists who have won this prize. So there are 3 brilliant scientists who has been awarded with the Nobel Prize in 2025 in chemistry. First is Richard Robson. He is professor at University of Melbourne, Australia. He was born in Goosburn in England in 1937, and he did his PhD from Dyson Perrins Laboratory, which was part of Oxford University that time, in 1962. He is the oldest guy out of 3 people. And the next is Susumu Kitagawa. He is professor at Kyoto University, Japan, and he was born in Kyoto in 1951, and he did his PhD from Kyoto University in 1979. And the third scientist is Umar M. Yaghi. He is professor at University of California, Berkeley, USA, and he was born in Amman, Jordan in 1965, and he did his PhD from University of Illinois in 1990. So before I introduce what is MOF, how they look like, how they are synthesized. I want you to get introduced first to the problem. What was the problem that these three people were able to solve? So what was lacking? What was missing in chemistry that these three people were able to achieve? So I will start with the problem. So imagine I have a bulk solid material. I have a solid material. Imagine I have a brick, okay? And this brick has a magical surface. It can do some reaction on it. I bring some reactant, some molecule. It get attached to this surface, and it react. It form a product which get dislodged. So this brick, the surface of this brick is doing reaction, is driving a reaction, or I can say more accurately, it is catalyzing a reaction. Now, let us think, so this brick is a solid molecule, but only for my reaction, only the surface, the outer surface is being utilized. The material which is present inner side of this brick is not getting utilized. The surface is only getting utilized. The same material which is present inner side beneath the surface is none of our use. But as a chemist, I don't want that. I want all the materials to get participated in my reaction. So how can I do that? I want accessibility throughout this brick. So how can I get that? So a lame idea is, why don't I drill this brick? I do drilling, I put holes, or I could say pores, and I make a porous material. So I have gone from solid to a sponge-like material. Now the reactant can travel all the way through these pores, and whole material is being utilized in a reaction. Okay, so this is the beauty of porous material, that they catalyze reaction in a much better way. Imagine this was doing reaction in 1 hour. This may do in 10 minutes or maybe lesser. So it will increase the reaction kinetics. So that's why scientists or chemists have always been interested in developing porous material. But to imagine drilling a brick is practical. But imagine drilling a molecule. It is not practical. You can't drill a molecule. So what we can do at molecular level, what we can do? So we can't go from here to here at molecular level. But what can we do is, but what we need to do is, we have to start by this porous material itself. Imagine when a building is being constructed. The building is being constructed in such a way, so they don't build a whole block of building and then drill rooms or flats in it. But they build in such a way that spaces for the flats, for the rooms are created at the same time when building is made. And this is the approach we have to also apply at the molecular level. We have to build the molecules in such a way that these holes, these pores are created at the same time. So this is the approach. And what could be the possible application of this porous material? One, as I said, that it will catalyze our reaction in a much better kinetic way. Second is, imagine I want to store something. This molecule have a lot of spaces, a lot of rooms in it, so it can store something. So it can be used to store some gases or some molecules. And third application of this molecule can be, it can act as a sieve. Imagine we use chalni in our day-to-day life. We separate tea leaves from our liquid tea. It can do so. So if I have a mixture of molecules in that, if some molecules have size lesser than this pore, it will go through it. But bigger size molecules will not. So it will separate the things out. So these are the 3 points I want to highlight, that it will provide a high surface area, it will be accessible. Second is, it can be used for gas storage. And third is, it can act as a molecular sieve. But now, the challenge is that these pores can't be of random size. As a chemist, I want them to be of exactly same size. Why? Because if they are of different size, they will behave differently. So they will not behave in a similar way. But I don't want that, because if they behave differently, then they will not do one thing for me. They will do multiple things, and I don't want that. I want this material to do one particular thing for me. So these pores should be of exact same size. Like in a building, all the flats, if it is a 1 BHK, they are all similar size. In the similar manner, I want these pores to be of exact same size. So this is the challenge to do that. Imagine at a molecular level, a molecule that we can't even see, it is that tiny. So to do that, it is very challenging. So when I talk about building something, in chemistry, we mean synthesizing something. And for synthesis, what it means, we want to make bond between atoms. So in chemistry, when we want to synthesize something, it means making bonds between the atoms. And you may have heard about ionic bonds, which is present like in water molecules. It is ionic molecule. Ionic bonds are present between oxygen and hydrogen. And there is a new category of bond which is present between metals and organic molecules. So when a metals binds to an organic molecule, it forms a very special kind of bond, which is called as coordination bond. So it is a metal molecule coordination bond, and it is a separate field in chemistry which is known as coordination chemistry. But I will not go very detail about coordination chemistry. But the point is that metals and organic molecules, the bond is very different from ionic bond, and it is categorized as a new bond, which is called coordination bond. And not all the metals can form this coordination bond, but there are some specific metals which can do that. And those metals are present at the center of the periodic table. They are called D block elements, or they are called transition metal elements. They, when binds to an organic molecule which is made up of carbon, nitrogen, oxygen, hydrogen, when metals binds these molecules, they form the coordination bond. But now so imagine I have a metal. Yes.
You said the bond is normally the bond, the electrons are shared between the two atoms.
Yes.
So this electrons are shared.
They are actually donated by one to the other. So
so it's not that both people share electrons. Electrons provided by the same
molecule. Yes. Yes. What happens in? So in ionic bond, imagine H2O, water molecule. So hydrogen has donated its one electron to the oxygen. So hydrogen has lost its electron, so it is H plus, and oxygen has gained one electron, it is O negative. But this is not the scenario in case of coordination bond. So in coordination bond, it is very actually, so metals, which these metals, when these metals came across to the organic molecule, these organic molecules donate a pair of electrons. The two electrons are donated by the organic molecule, and they are donated to the hybridized atom, hybridized orbitals of the metal. It may be a bit complicated for you, but in the easiest way I can say that this is not an ionic bond. This is not like it has it is not like it is this is positive after donating and this is negative. This is not, this is a bit different than that. Okay, so imagine yes. So it is a kind of ionic force. It is a kind of ionic force. It is an attraction force between the organic molecule and metals, and the electrons are donated from organic molecules to the metal. So metal is slightly positively charged and organic molecules are slightly negative charged, and so they are bonded together with an attractive force. Yes. Yes. So yes. Huh. That's about the electronic properties of that metal, and that's why the transition metal elements are able to do that. So it is about the how the electrons are filled in that metal. So it is about the electronic properties of that metal, that not all the metals can do that. So these metals have empty d orbitals. That's why they are d block elements. They have empty d orbitals which can take electrons from organic molecules. So that's why they are special to form coordination bond. So like in water molecule, oxygen binds to 2 hydrogen atoms. In coordination bond also, it is not like it will form only one bond between metal and organic molecule. This metal can binds to multiple organic molecules. So it can binds to two organic molecules, it can binds to 3 or 4, and it will depends on what metal you are picking. So if you pick a metal which can binds to 2 organic molecules, it will form a linear geometry. And if it binds to 3, it will form a trigonal planar molecule. And if it binds to 4 organic molecule, it can form tetrahedral structure like that, and it can form square planar. And it can binds to higher number of organic molecule as well, 5, 6, 7, etc. And if we look at this structure, metal binded to organic molecules, they are classified as zero-dimension structure. And I would say why they are classified as zero-dimension structure. A dimension is defined when something is extended in a directional way. Imagine this molecule. This is extended in a one direction. So it is 1D structure. But these molecules are not extended. They are just a single molecule. Imagine if they are a spot or a dot. So they are classified as zero-dimension structure. Now, idea is, so remember our problem. What we want to do? We want to make a molecule which is porous and which is a framework. Remember the picture I showed in my earlier slide. So if I want to do that, why can't I start with zero-dimension structure, and I can stitch them together to get higher dimension structure. Imagine I have an organic linker. So imagine I have this organic molecule which can bind to 2 metals. If it can bind to 2 metals, then I can stitch them together. And if I can stitch them together, then I will get a 1D structure. So if I stitch them together, I will get a 1D structure. And if this 1D structure is extended, then I can get higher dimension structure as well, 2D, 3D. And this was the idea, and it is not my idea, but it was the original idea of our first scientist, Richard Robson. So he was teaching his students in University of Melbourne, Australia, and he had to develop some wooden models like the same I am showing here. So he was developing some wooden model to teach his students for helping them out. So what he realized that atoms binds so the holes placed at the ball are at very specific position. These holes are not random, but they are at very specific position that atoms bind in a very specific geometry. And his idea was, why don't we utilize this property of atom for the metal and molecule? So the metal and molecule can bind in a very specific manner, and they can be stitched together to generate higher dimension structure. So this zero-dimension structure, if we start with metal and organic linker, if we stitch them together, we can get a 1D structure. If this organic linker is able to bind to multiple metals, so then we can generate a 1D structure, and it will goes on. And now think if this organic linker is also able to bind to the next metal present at the top. If that is possible, then we will get a 2D structure. Now imagine this organic linker present here is also able to bind the next metal present at this side. Then we will able to get a 3D structure. So this was the idea of Richard Robson to stitch 0D structure together, 0-dimensional structure together to get a 3D structure. And he also actually tested it out, and he tested it on a metal which is copper ion and an organic molecule which is which has 4 donating sites. So this organic molecule can donate from 4 sides: 1, 2, 3, and 4. It is a nitrile group. It can donate from 4 sides. And this copper ion can also bind to the 4 site. So this is the copper ion. It can bind to 4 site, 4 organic linkers, and each organic linkers have 4 donating sites. So he was actually trying to mimic a diamond-like structure. In diamond, carbon have bond with another 4 carbon atoms. So he was actually trying to mimic that diamond-like structure by using a copper ion, which can bind to 4 organic linker, and an organic linker which has 4 donating sites. And what he actually got was very mind-blowing, because he actually got the diamond-like structure. It was indeed a diamond-like structure, and it was a 3D network. And very amazingly, he had these cavities, this porous area, this space that we were talking at our initial stage. So he was able to synthesize this 3D structure which had this porous or I would say cavities. And now look very carefully. These cavities are exactly of same size. They are not random. They are of exact same size. And this is the beauty of this material. So it was a crystalline, it was diamond-like, it was an extended framework, and these cavities were filled with the solvent molecule in which it was synthesized. So it was filled with solvent molecule or any counter anion. And he showed that this solvent molecule and anion filled in this cavity are not really stick to this cavity, but they are moving. So these ions are moving throughout this cavity. They can travel through it. So the diffusion of molecules and ions were possible through this cavity. And that's what we want. We want things to not to get very stick, but to move. So we can utilize this cavity. So then, yes. Counter ions are, so it is synthesized in a solution phase. So in solution phase, whatever additives you have used, the counter anions can also counterbalance. So in this case, it was BF4 negative, tetrafluoroborate. It was the counter anion. So they were present at these cavities. So now if we want to use this cavity, so I don't want it to get it to be filled with solvent molecules. I want to utilize this cavity. Imagine I want to store O2 in it. So first I have to evaporate solvent out of here. Then I can utilize this cavity for something else. So when Richard tried to evaporate solvent by heating this material, it actually collapsed. So it was not thermally stable. So when as soon as you start heating and removing this solvent molecule, it get collapsed, it fall apart. So this structure was not thermally stable. But Richard was able to showcase this idea, and when he showed that it is not stable at certain after certain temperature, scientists at that time thought that this is waste of time. This is not useful molecule, and they really didn't give attention to it. But there were few peoples which were interested and which were believing that this can be useful and this can be made thermally stable, and it can have potential application. And out of these few peoples who were believing in Richard, one of them were Susumu Kitagawa. And his motto was that even useless thing can be useful, can become useful. And he was working on this metal organic molecules, coordination molecules for a very long time. And this was his major breakthrough when he synthesized a cobalt, when he synthesized this molecule using cobalt metal and an organic linker, which is 4,4-bipyridine. So it has 2 donating sites. This 2 nitrogen can donate to the cobalt. And the structure he obtained was this. So in which the cobalt is here at the center and it is connected to the rings, these rings, to the nitrogen. And he called it a tongue and groove structure because this tongue is fitting to the next groove present next to it. So it was a tongue and groove framework he called. And if we look a graphical image of this molecule, so this is how it look in a graphical image. And this yellow thing, this actually represent the empty area present here. So like in Richard case, the empty area was like a space, a 3D space, a ball-like space. But here it is like a channel, a full through a whole go through channel in this molecule. And this structure was thermally stable. So it was not collapsing when you tried to evaporate the solvent. So it was the first thing which was stable. And he actually showed that it was able to store methane gas, nitrogen gas, and oxygen gas. So this was the major a breakthrough study in case of these 3D porous molecules, that they can be useful and they can be applied for the absorbing gases like small molecules. And then so Richard's in previous slide I showed Richard's molecule. So it was thought that that molecule is useless, because when you try to evaporate the solvent, it is collapsing. So you can't use that for your application. So that's why people thought that it is useless. But Kitagawa believed that useless things can be useful. They can be somehow made useful. So the next thing Kitagawa was able to do is he was able to show that these 3D structure that we are talking about, they are not rigid. They are not like the building we live. They are not very rigid, but they are flexible. In presence of external stimuli like pressure, temperature, or anything else, they can change their morphology. They are flexible. They are behaving like the human lung. When we inhale, when we exhale, the shape of the lung changes. So it is called. So he called it a molecular lung, which can shape accordingly and which can change its morphology accordingly. And then let's come to our third scientist, Omar M. Yaghi. So Omar M. Yaghi was the one who coined this name, metal organic framework. Yes. Huh. So it is estimated by some techniques, which BET is the technique. Using that, the surface area is calculated for this porous material. Yes.
The molecule is far bigger than the space created. How do we say that it fits it? With the earlier slide.
Yes.
Say that the different molecule can fit in the gap created.
Yes.
Like the impression is bigger than the gap. How is it? How can one imagine the thing fitting in the? So
question is that methane molecule is bigger than.
Is it not bigger than?
No, it is not bigger. So these cavities are, these are microporous material. So these cavity size are around 1 nanometer. The methane molecule is smaller than that, and it can fit. Yes. So now let's come to our third scientist work, Yaghi, who coined this metal organic framework term. Before that, these molecules, the Richards molecule, Kitagawa's molecule, were known as coordination polymer, because they have coordination bond, and they are polymeric because they are networking. So they were called coordination polymer. But Yaghi was the one who gave this terminology, metal organic framework, because they have metal, they have organic part, and they are a framework. So that's hence come the name metal organic framework. And he was also working at parallelly at the same time period of Kitagawa. And his major breakthrough was this study in which he chose metal zinc, and the organic linker he chose is 1,4-benzene dicarboxylate. It has 4 donating sites, 1, 2 oxygen here and 2 oxygen here. So it has 4 donating sites, and when it binds to the zinc, it forms a structure like this. So it's the same structure. So this is the single unit. When it is repeated, it forms a 3D network, 3D framework like this. So this is the metal, this is the unit, the same unit here, and this part is the linker. Okay, so this is the linker. Now, if you look at this structure, we can see that as compared to the metal side and the linker side, these cavities, these walls are huge. They are of very huge size than if we compare to the metal side and the organic side. And when he actually calculated the surface area of this structure, the number was actually very high. So the surface area of this MOF was 2,900 meters square per gram. Imagine 1 gram of something. This is not MOF, but this is sugar. So this much is 1 gram. It can have surface area equal to 2,900 meters square. This number is very similar to a football pitch. So imagine this much of compound can have surface area equal to a football pitch. Now imagine how much gas it can store. How it will catalyze the reaction. It will be much, much faster than as compared to the traditional way. And it was very highly thermally stable. This structure was stable to the 350 degree, which is huge. So it was very stable and such a large surface area was present.
Microporosity becomes important only when something gets absorbed.
Yes.
Otherwise, it is not absorbed.
So so it depends on the application. So they are useful when you apply them for something. Otherwise, yes. Yes. Correct. So till today, this is the most famous MOF reported. So now imagine this molecule is able to store H2. Let us suppose, yes. Here, so why it is shown like that? Because when you look at here, all the oxygens are binding to the 2 side. So this oxygen is binding to the 2 side. This oxygen is also binding to 2 side. Yes. No, it has to be organic. So why this oxygen is shown like that? I am explaining that. This oxygen is basically this oxygen, which is actually certainly in a different environment. This oxygen is binding to 4 metals. So this is in a bit different environment, and that's why it is shown like this. But the zinc is binding indeed to the organic molecules. Yes. So now imagine this molecule is able to store H2. Okay. Imagine this cavity can fit H2 only. But if I want to use it for, let's say, CO2. CO2 is a bit bigger than H2 molecule. Then I will want a cavity which is bigger than that. Because CO2 will not get into this cavity because it can't fit. Okay. So we want to increase this area so that it can fit something bigger. And if we want to do that, what can we do? We can increase this length. Then this area, increase this length, we have to actually increase the length of this side to fit something bigger. This was the idea of, okay. So this was the of Yaghi, and he was actually able to synthesize, he was actually able to tune these cavity size. We go from here to here, when the linker is bigger, this cavity size is bigger because now the linker is extended. From here to here, the linker is extended, so the area is now bigger. And if we go to the 3 benzene ring molecules, then it is increased accordingly. So it is a very controllable thing, and it is very programmable. So even before entering lab, I can decide what I want to synthesize. I can decide what application I want, and I can synthesize the MOF accordingly. So it is very programmable. So it is not an try and error thing. It is very controlled and very programmable. So this is the beauty of MOFs that people were excited, and why they won this year's Nobel Prize. So I hope I am able to convey that. And look at these structures. These are all MOFs, and they are not rangolis. They are not just designs, but they exist in real life, and they all do some different kind of work. So MOF 303 is used to harvest water. So from the air, if you want to harvest water, so this is useful for desert area where water crises are there. So it can harvest water. Now this MIL 101, it can store H2, CO2. Then UIO 67, it can separate. So I also talked about separating things. So it can do that. Then for rare earth mining, CO2 capture, H2 storage. So there are different kind of MOFs being generated depending on what application you want. I'm not very expert about metals mining, but I'm sure they are doing it with the help of these cavities to sort out the metals. But metals mining, no, this is useful because yeah, it is about taking something out of a mixture. So for mining, it is also useful. So if we compare MOFs to the compounds which existed before their discovery, like geolites, silicas, or activated carbon, if we look at the number of surface area that they provided, so geolites had less than 1,000, and silicas equal to 1,000, and activated carbon, they are slide size. Okay, but I have to go back, I think. Yes. Is it okay now? Okay. So zeolites, it's less than 1,000. The surface area they provided. For silicas, it is almost 1,000, and then 1,500 or something. Yes, till date, before MOFs came out. Now look at the area that MOFs are providing. It is huge compared to these traditionally existing materials. This is huge. And the highest area, surface area being reported is around more than 7,000. So which is very huge as compared to the geolites and silicas. Sorry? MOF. No, this is after this. So yes. Yes. To 2012. Because so molecules were being synthesized, but it depends on how we are applying them, how they are being useful. So Nobel Prize is given not when something is synthesized, but if this is able to solve some problems, it is being useful at some point. So when the science, the MOF science grew, and they were able to apply it for various kind of applications, and I believe that's why it is a bit late, but yeah, it deserves. Okay. So if we look at the numbers of reported MOFs, the MOFs being reported every year. So if you look here, there are almost very few papers were there on coordination polymers. So in 1995, Umar M. Yaghi has started, and these reports were out. And look at the number of reports, they are increasing. So people are now exciting and interested in development of MOFs and their application. So if I come back to the application, so right now we don't see MOFs in our day-to-day life. They haven't entered our day-to-day life yet, but these molecules are being tested for separation, for separating pollutant from water. They are for gas storage. They are being applied, and at pilot plant levels they are being used. Even for drug delivery and drug storage also they are being used, and for catalyst and separation, as I talked. Sound absorption. They are being used for air purifier. If you want to purify air, हाँ हाँ हम्म हम्म
The same way the
No. No, I'm not aware of such things that they are being used for sound service. But air purifier, they are being tested. Yes. So maybe in near future, we will able to see MOFs in our day-to-day life somewhere. And if you want to read more about MOFs, you can go through some reports, some papers published by those three brilliant scientists. And now coming to what I do in my lab at TIFR. So I work in a material chemistry lab and I am working on CO2 conversion. So CO2, the anthropogenic CO2, which is emitted by ourselves in the environment, which is harmful because it is causing global warming. And right now the concentration has, the CO2 concentration is more than 430 ppm in environment, which is alarming. And so the research is going on if we can convert this CO2 to something else that can be useful. So we can reduce the CO2 emission in the environment. Yes? Yes. So for that, the techniques which are being used for CO2 conversion are photochemical techniques. You give light and you can convert it to something else. You can do thermal, you can heat it with something else and convert. And one technique is electrochemical. You provide electricity and for electrochemical cell, there is CO2, there is some other molecules, water, and you can convert it to something else. So that is called CO2 conversion. So these are the problems that we are dealing to, why we are dealing with CO2. And CO2 can be utilized using electrochemistry. So in electrochemistry, in a cell, we take electrodes, we put waters, we purge CO2 gas, we provide electricity, and then CO2, when it takes protons from water, it is converted to carbon monoxide, which is very useful synthetic gas. Formic acid, methanol, ethanol, and there are various type of fuels and chemicals which can be generated. And another way is we can react this CO2 to an organic molecule using electrochemistry, and we can synthesize carboxylic acid, which are very useful. They are some drug molecules based on carboxylic acid, and there are various type of antimicrobial agents and being used in industries. So we can do that also. So I work on electrochemical CO2 utilization in my lab. This is all about me. Okay, thank you.
The CO2 is there a unit and cost right now in your CO2 emission? Are you including cost?
So I am not working on MOFs. I am working on metals, but MOFs are also being tested for CO2 conversion. Yes, they are being tested.
How would that affect?
So in electrochemistry, there's a cell. You put an electrolyte, then you dip two electrodes and connect it to an electricity. So you have to make an electrode for that. So you have MOF, which is a powder. You make an ink out of it. You just pour it on an electrode. You make it, you dry it. You make it solid. Then just put it on solution. Provide the electricity. The things will happen. It is not reversible. No, you permanently convert it to something else.
No, but there is no conversion in this case. So when you are working with the absorption material.
No, there is no conversion. That is separate thing. That there is no conversion. This is reversible. You can absorb the gas. You can dissolve the gas. This is reversible. Yes. It is reversible. You can undo that. Yes. Yes, exactly. That is undoable. This is permanent conversion. No. They are synthesized at certain temperature. They are stable at certain temperature, but you don't have to store them at depending. So generally MOFs are at they are stable at room temperature. But I don't know if there is any specific MOF which needs to be stored at some certain temperature. That can be a case. But generally they are room temperature stable. Yes. Any question from them?
Yes, so let me just take the online question. How do you estimate the surface area, so many meters squared per gram of water you said?
So
You said some BET. Can you explain how is that really estimated?
So in BET is a technique in which so imagine I want to estimate a surface area of, let's say this. So what will I do? I will give a known amount of gas to it. Let's say I gave let's say 5 gas, and then if I get 4 gram of gas, then of gas is adsorbed to this material, and I got 4. So 1 gram is missing. So that means that is adsorbed. So there are isotherms, there are theorems by which you can calculate the surface area. But the the strategy behind this calculation is this, that you give some numbers, you get some number, and out of this is the thing that gets stored in that molecule.
Okay, so since there are no more online questions, I'm going to end the online stream and then we can do it through this program.
Okay, thank you.
Yes, sir.